What's up everybody, my name is Eric. Welcome to my channel, Eric the Tutor. What's up everybody, my name is Eric. Welcome to my channel, Eric the Tutor. Today, I'm going to give you guys a nice chart for tackling SN2, SN1, E2, and E1 problems, okay? So this video is going to be kind of quick because I'm just going to go through the chart. I want you guys to note it down and then start to add to this chart and build your own chart. I recommend seeing different examples and adding it to the different columns and making it unique to yourself, okay? So on our left here, we have primary, secondary, and tertiary, which is the substrate. So we want to consider whether the substrate is unhindered or whether it's hindered. And that's going to determine if it's going to be more SN2 and E2 versus maybe SN1 and E1, okay? So that's the first thing you want to look at when you're doing those problems. The next thing is you want to look at your nucleophile. You want to determine if it's a poor or a good nucleophile. And the way to do that is to determine if it's a poor nucleophile. I like to think of a football game and somebody went streaking at the football game. So in order to be a good nucleophile, let's say they are a good streaker. So here would be a good nucleophile. Now notice this would be the streaker and the Na plus out in front is just the spectators in the crowd. So they're not going to do anything to stop the streaker. And for this to be a good streaker, he has 3 lone pairs around him that is able to go out and do nucleophilic attack. It's able to donate its extra electron density. Now you can notice if I were to draw something that looked quite similar, here I have an OCH3 and an OCH3. How are those any different? How is one considered a good nucleophile and one considered a poor nucleophile? Well, you can see that this streaker has pants on. So it physically has a bond to the hydrogen that's preventing him from being a good streaker. You can think of the hydrogen as being the OCH3's mom, and the mom's not letting her son go out and do that kind of thing. So this would be a poor nucleophile. Notice it only has 2 pairs of electrons. Only has 2 pairs of electrons, so it's not as electron rich. I could have given you something like H2O, which would have been another example of a poor nucleophile. Only 2 available alone pairs. And if I wanted to give you another example of a good nucleophile, I could have given you OH minus. Okay, so that's the second thing you want to look for. You want to look at the substrate, and then you want to look whether it's a poor or a good nucleophile. Now notice, if we have a good nucleophile, that's not good enough to characterize whether we're going to get SN2, SN1, E1, or E2. We have to look even closer. So we have to determine if it's a weak base or whether it's going to be a strong base. Now over here I have strong bases. Now whether it's going to be big and bulky versus small is also going to give you different results. So I listed some examples down here. If you have a big, bulky, strong base such as LDA or terbutoxide, then we would expect to see more E2 reactions. Then if we had a smaller base like OH minus or OCH3 minus, OR, these are going to give us E2, but we could expect to see more SN2 products because of how much smaller it is. So it can actually do that substitution. And then here I have the weak base column. This is the CO minuses, the BR minuses, CN minus, SH minus. Notice how many more SN2 products we get, okay? And then our poor nucleophile column, we have water, CH3OH, even a carboxylic acid can use its OH, and we can expect to get a mix of SN1 and E1 products. Okay, so start to use this, and we're going to go ahead and do many more examples in the next videos, and you'll be able to apply this to those problems. Thanks, guys. See you next time.